Hello, welcome to this video. This is 8-2 and we are talking exponential growth and decay. And we're going to go ahead and look at some problems where we're going to generate formulas talking about exponential growth and decay. Alright, so mathematical models in which the rate of change of a variable is proportional to the variable itself are common in both business and scientific worlds. So suppose you have a rate of change with respect to time, so dy dt. Is proportional to y itself, okay? And k is what we call the constant of proportionality. Can you say that? Constant of proportionality. And then y is the amount of a substance. It could be talking about like a radioactive isotope. It could be talking about population. Just something that we measure in business or in scientific worlds. And then k would be its proportionality, okay? So what we're going to go ahead and do is we're going to solve a general formula which we will kind of use often from this idea, right? So if I have dy dt is equal to ky, and what I want to go ahead and do is I want to solve the variables and solve the differential equation. So I'm going to go ahead and move over y, so I'll divide both sides by y, and I will multiply both sides by dt to get 1 over y dy is equal to kt. Okay, so now I'm going to go ahead, I will integrate, and we get the natural log of the absolute value of y is equal to, so I'm supposed to be a dt, so kt plus c. Okay, and now what we'll go ahead and do is I'll introduce e on both sides. So we get the absolute value of y is equal to e to the power of kt times e to the power of c, which gives us y is equal to plus or minus c times e to the power of kt. And since I have plus or minus a c, I can just call that again a c, and we get our equation. So y is equal to y is equal to c times e to the power of kt. All right, and what we have here is a basic law of exponential growth or decay. So there is our function. All right, so some constants that we're going to look at in this formula. The c value, that's often known as your initial value or the amount of substance present at time t equals 0. K is the constant of proportionality. And what we're going to do in these problems is go ahead and solve for these values. Variables, t, that's the variable of time, and then y is the amount of substance present at time t. So it's dependent upon the t value, right? The time that it is. Okay, so let's go ahead and look at a problem. What is the rate of growth of the population in a city whose population triples every 100 years? Assume that the population growth can be modeled by the basic law of exponential growth, and express your answer as a percent rounded to the nearest hundredth of a percent. So when they say the basic law of exponential growth, they are telling us that the function here is being modeled after this model here. So c times e to the power of kt. Okay, well, what they told us in the problem is that the rate of growth of the population triples every 100 years. So if a population starts out at c, okay, in 100 years, so when t is 100, right, that's what they tell us here, then it will be 3 times that amount of population, so 3c, okay? So what we can go ahead and do here is we can go ahead and solve for k with this information. So we'll go ahead, we'll divide both sides by c, and we get 3 is equal to e to the power of 100k, and I want to solve for k, so I'm going to go ahead and need to undo the exponential by taking the logarithm of each side. So I have the natural log of 3 is equal to 100k, and then we'll divide both sides by 100, to give us K, which is approximately 0.0110. Okay, and as a percentage, if I go ahead and we just multiply this percentage by 100, we get 1.10%. Okay, and that is the percent. Okay, so there we go. There is the population growth. All right, example 3. Here it says, let Y represent the mass in pounds of a radioactive element whose half-life is 4,000 years. If there are 200 pounds of the element in an inactive mind, how much will still remain in 1,000 years? Express your answer to 3 or more decimal place accuracy. All right, so with this problem, what we're going to have to do is go ahead and do a couple of things. We're going to do what we just did in the last problem. So they say that the half-life is 4,000 years. That means it takes 4,000 years for the amount to be cut in half. Okay, so I have an amount. Let's call it C. Okay, and then after 4,000 years, there is half of C. All right, okay. Next, what we're going to go ahead and do is I need to go ahead and solve for K with this model. So I'm trying to identify what that growth or decay rate is. So we'll divide both sides by C. So 1/2 is equal to e to the power of 4,000 K. I'll take the natural log of each side, and then I'll go ahead and divide by 4,000. So 1 over 4,000 is equal, so 1 over 4,000 of the natural log of 1/2 is equal to K. And this is approximately negative 0.0002. Okay, so there is my K value. Now I'm going to go to the next part. So the next part, they say, is if there are 200 pounds of the element in an inactive mind, how much will remain in 1,000 years? Okay, so I'm going to go ahead. I'm going to take my function, y is equal to c. Okay, so how much is there of the substance? Well, 200 pounds. And I want to know 0, 0. Whoa, the lights went off. Man, hate when that happens. So we get negative 0.002 times 1,000. Okay, so again, all I did was plug in 200 for C, right? That's how much is present. And then I'm going to plug in 1,000 years, and I want to figure out, okay, well, how much is going to be present? So if we plug this into our calculator, and they want it to 3 or more decimals, we get 168.179 pounds. Okay, and there is your answer. All right. I'm going to go ahead and end this video. The second video will focus on Newton's law of cooling. All right, catch you next time. Peace.